This video is brought to you by the ILC. For questions like these, it's important we understand the terminology present. So for instance, for part A here, it's asking about critical points, relative minimum, relative maximum, and neither, which makes sense. So what is a critical point? So a critical point is defined as the point on a function on which, let's write this down. So critical point is a point, usually an x value. So x value for which f of x, or rather f prime of x, equals 0 or does not exist. Let's find out where those points are. We have f of x. So let's find f prime of x. Luckily, f of x is just a polynomial, so the derivatives are a simple power rule derivative. That is 3x squared plus 2x minus 5. We need to find where this is equal to 0 first. So we set this equal to 0, set 3x squared plus 2x minus 5, and we can factor that. I believe that'll factor to 3x plus 5 and x minus 1, I believe. All right. Since this is equal to 0, we have two factors being multiplied, or that are equal to 0. That means we can set them individually equal to 0. That tells us that when 3x is equal to negative 5, or in other words, when x is equal to negative 5/3, or when x is equal to 1, that the f prime is equal to 0. That covers the 0 case. How about DNE? Well, polynomials, and such as quiz quadratic here, actually always exist. Right? So there is no point at which they do not exist. There is no vertical asymptote or anything like that. So the DNE case does not matter for us, and we just care about these two numbers here. These are our critical points. So for us, x equal to negative 5 halves and 5/3 and 1. All right. Questions also asking the intervals on which the function is increasing or decreasing. Since we're dealing with a polynomial that has no undefined first derivatives, we would have to simply check the values in between our critical points. Specifically the first derivative. So f prime, draw a little number line here. We have negative 5/3 on one side and 1 all the way over here. A number in between those is something like 0. A number past 1 is something like 2. And a number less than 5/3 is like negative 2. When I plug that into my f prime of x here, and I can plug that into either the factored version or the unfactored version up here, I'll use the factored version personally. So negative 2 times 3 is negative 6, plus 5 is negative 1. I could even write that down here. Negative 1 times negative 2 minus 1 is negative 3. So it's a negative times a negative, which is a positive. Note that we only care about the sign here. 0, I would actually plug that into the original equation because now I can tell it's just negative 5. And when I plug in 2, I have 6 plus 5 is 11. And 2 minus 1 is 1. So a positive times a positive is a positive. And as we all know, a positive first derivative corresponds to an increasing graph, and a negative first derivative corresponds to a decreasing part of the graph. So I'd say increasing from negative infinity to negative 5/3. Oops, let's make that fraction bar a little better. Union 1 to infinity. How about decreasing? It'd be decreasing from negative 5/3 to 1. All right. We can use this information to easily identify each critical point as a relative maximum, minimum, or neither. Note that relative maximum, relative minimum is also called a local maximum or local minimum. So just another word for the same thing. A minimum, a relative minimum, is a critical point for which the slope is decreasing on the left and increasing on the right. You can see how this forms a minimum. And a maximum is increasing from the left and decreasing on the right. You can see how that would form a maximum there. So minimums can be found decreasing on the left and increasing on the right, so at 1. And maximum can be found increasing on the left and decreasing on the right, so that is negative 5/3. All right. Now that we've identified each critical point, we can simply provide those as our answers. We'd say this is a min and this is a max. Or circle these answers down here. That's part A for us. Let's look at part B then. So part B says find the inflection points and give the intervals on which the function is concave upward or concave downward. So inflection points, that's another vocabulary term we're going to have to memorize. Inflection points specifically are really similar to critical points. It is another x value, specifically where f double prime of x is equal to 0. Knowing this, we can simply find where f double prime of x is, what it is, and set it equal to 0. So if f prime is equal to this, then we take the derivative of that. That is 6x. Go scroll down, we have 6x, and now let's scroll back up and plus 2. Oops. Sometimes I accidentally scroll there. There we go. All right. So we want to set this equal to 0 in order to find the inflection point. So we have 6x plus 2 equals 0. When we subtract the 2, we have negative 2 equals 6x. And then we divide by 6 to get negative 1/3. We found the inflection points, but we need to say whether we need to provide the intervals on which the function is concave up or concave down. And this is a very similar process to find increasing and decreasing with the first derivative, except this time we just use the inflection points and the second derivative. I have negative 1/3 right here. Before negative 1/3, if I plug in, let's say 0, or excuse me, negative 1, and after 1/3, negative 1/3, such as 0, I can plug those numbers into here in order to find whether it's increasing or decreasing into our first derivative. When I plug in 0, I get 2, which is positive. When I plug in negative 1, I get negative 4, which is negative. A negative second derivative corresponds to concave down, and a positive second derivative refers to concave up. There we go. So in other words, it is concave, write this out, concave down from negative infinity all the way to negative 1/3, and concave up from negative 1/3 all the way to infinity. Note that these will almost always use parentheses. In fact, I can't think of a case in which increasing and decreasing intervals would use brackets. Last thing to do is sketch the function, which is really just connecting the dots here. We want to label the points at which this function, we know the values at, and also if we're looking at the function, we say be sure to label coordinates, coordinates of critical points, inflection points, and y-intercept. Notice they say coordinates of critical points. Now, when we say critical points and inflection points, generally we're referring to an x value and a y value. So that's something we missed earlier, is that we need to find the corresponding y values here. That means we need to take our numbers and plug them into the original function. The negative 5/3, the 1, and the negative 1/3. Now, luckily I've already performed these calculations. F of negative 5/3 is equal to, and let's check my actual calculations here. We have 92/27. f of 1 is negative 6. And f of negative 1/3 is negative 34, 27ths. It's 34. Note that 92/27ths is roughly 3.48 or 3.5. And negative 34/27ths is roughly negative 1.5. These are just estimates for our graphing purposes. That way when I graph it, I see that we have a few points on here. 1, negative 6, which is way down here. We have the point negative 5/3, so almost negative 2. Negative 5/3 and 3.5, so maybe here-ish. Again, we're just kind of sketching the graph. We're not trying to be perfect about it, just good enough. And finally, negative 1/3 and negative 1.5, so somewhere about here. There we go. All right. Now, at negative 5/3, it was a maximum, and at positive 1, it was a minimum. Note that the graph, in addition to saying the critical points and inflection points, but we also need the y-intercept, so when we plug in 0 into our original function, that'll find the y-intercept for us. F of 0, when I plug in 0 into the original function, that's actually the easiest one, because all the x's go away, and we have negative 3. 0, negative 3 would be somewhere around here. All right. Maybe a little bit lower. So that's negative 3.5, right? Or negative. It's negative 6, so it's about halfway to that. So about there. They're just sketching. I'm just being particular. All right. Just to connect the dots here, it looks something like maybe a little bit better. Like that. Since we've sketched the graph as they asked, then we're done.